Hello everyone, I want to welcome you to my YouTube channel. This is Steve coming back with another video for the Commodore 64. In this example, we're going to be exploring the machine language tutorial for the Commodore 64, Part 4. Now the last video I put up here was actually around June. I think it was June 24th if I recall. And at that time, I was moving along talking about the load and the store values and showing how you can pass values into the load accumulator. And then once you have those values saved in the accumulator, you can transfer them into memory, like absolute memory, so that you can get results on the screen or just write values to memory alone. So I wanted to stay consistent with that, and just instead of moving too fast forward, I don't want to kind of jump in big segments and say, okay, let's cover the load, store, and let's go to index and this. I'm trying to break this up. The way you would actually learn this in machine language is step by step, on a step-by-step basis. This is very important because machine language isn't going to be, you're not going to learn it all at once. You're not going to go in there and say, oh, I'll learn all the commands and now I'll get a game, I'll get a tutorial or whatever, running, a utility. No. You actually have to break it down into piece by piece, like a puzzle, putting together a puzzle or a Rubik's Cube or whatever you want to think of it, like building a car engine, for example. So step by step will allow you to learn as you're going up the ladder. As you start learning different concepts and you start understanding different techniques, you're able to add more advanced things along the way. So in this video, what we're going to be doing is moving to the next step, which is the index registers, and I'll be covering that with some examples. We'll be using, once again, my C64 to go ahead and produce results on the screen. And we'll be seeing examples. I also have an Excel graph I'd like to show you and break down memory and show you it as a decimal level, how it looks at decimal, how it looks at hexadecimal, how it looks at the petaxi or the screen memory, so that you can see the decimal for the screen memory and the hexadecimal value. So I really want you to understand this. And finally, it'll show you the text for the program. So first I'm going to show you that. So it might appear a little confusing at first, so stay with me, because eventually I'll put the program on the screen and piece it all together like that puzzle or that engine or whatever, and show you how it comes together to basically show you the complete result. So let's go ahead and get that started. Oh, and also before we start here, I wanted to share something with you that I've been trying out recently. I mentioned this in my other video, the Commodore 64 brain, the YouTube direction of where we're going and everything. Like I've been taking supplements kind of on the side here. This one is actually called Performix. I just got this at GNC. So if you have anxiety issues and you can't focus, I would recommend trying something like this. I kid you not, this is already working. And today I don't feel as less anxiety. You know, I don't have as much anxiety as I usually do. I can actually stop and think for a moment before moving on real quickly. So it's actually helping me in a lot of good ways. So let's get started. Okay guys, so as I mentioned in the last video, the last things we covered was the load and the store, and I just wanted to summarize on that. I think it's important so you can kind of, track off onto the next video. So here's the example of the load accumulator, taking the value of 3, storing it in accumulator's memory, and storing it into screen memory, hexadecimal 0400, which is essentially the decimal of 1024, and it places a C on the screen because 3 is actually the axi equivalent, or the petaxi equivalent for that, or the screen memory equivalent, if I'm saying that right. And then, of course, we got the RTS to return back to basic to exit the program. Otherwise, it just goes into a tight loop and it stays. And essentially, it doesn't do anything. It'll just crash your program. So I wanted to kind of cover that very briefly. Not to go into a lot of it. Watch the last video if you need more information on that. But that's where we kind of left off. Now, I also forgot to mention this definition, just to kind of throw that in there. So definition of implied, which we talked about, it's not a real addressing mode, but the destination is already implied within a command, also known as implicit. Okay, and moving on. So what is to come? Before we cover how to write messages or text on your screen, we needed to learn how to use the X and Y registers. This is a key component and is usually frequent in all assembly language programs. It allows you to run loops that can write data values to sprite memory, create animation, and lots of other things. Therefore, I have divided the following lessons into explaining how to use the index registers, the transfer X-Y registers, the arithmetic operators, the jump subroutine commands, and the X-Y accumulators. Understanding these mnemonics will give you some powerful tools to use as you begin evolving your grasp on a semi-language. The index registers. We will now be covering the X index register. This is an important register in a microprocessor. Keep in mind there is also a Y register, which we will cover below in the example part. And it's possible, guys, to kind of a side note here that I may split these apart. Again, not to try to cram too much at you at once. These two registers are 8-bit ones and contain a maximum number ranging from 0 to 255, or hex 00 to FF. They function similar to the accumulator, but mostly used as counters known as indexing. If you think about BASIC, they are nearly identical to the 4 next loops when combined with branching, to be discussed later. And also I said to be discussed later, but in this example, since we're going to go over the loops, we're going to be discussing those probably in this video. The contents of the register is used as an index or offset to an address. If the register value is 1, then 1 is added to a specified address. They can be used to also cycle through memory locations. This is handy when you want to print a line of text or characters to Commodore 64 screen memory, which we review further ahead. They can also be used as temporary storage. And of course, I'm going to show you what I mean by the screen memory. I'm going to give you examples. I mentioned about the Excel chart, so hopefully this is very clear to you at the end of this video. You can think of the index registers like a counter. It keeps track of a series of numbers that get passed into registers X and Y. If you recall, the load or LDA load accumulator is very similar in the sense that it is copying the value from the X register or the Y register and placing it into an area that can be used for later. Once this copy has taken place, then the values can be passed into memory locations to produce results. Let's first look at an Excel graph to understand this at the machine language level, and then we'll move on to a program example. We will be covering loops in this tutorial, as I mentioned, or otherwise the example won't make any sense. Excuse some of the advanced leaps here, but as you may recall, machine language is not easy to grasp and will take multiple iterations to get moving along at a comfortable pace. And that's where I was talking about those segments and those steps you take in the process. For now, though, we will see a loop example and write some text to the screen shortly. Okay, so before we do that also, I wanted to go over the LoadDX so you can kind of see it. I think maybe I'll say this, because if I go into this, you might kind of like, wait, you got top of the graph. So I'm going to jump back to that here in a minute. So I think I'm going to minimize this and just leave this in CBM Prg Studio in the background until we're ready for it. And we'll start going right into this. Okay, so what I talked about is I'm going to show you and break it down an analysis of how the computer sees things on the screen. Now, if you recall in the first example, we printed a C in the upper corner of the screen. I think we also printed a D, just to show you how you pass from the load value to the store. And when using the store, you're using memory locations 0400 all the way up, well, it's 1024 up to 1064. I can't recall the hexadecimals in my head. But essentially, that's screen memory broken down. And I think before we go into this, I'm going to give you a better example. Okay, so I had to scout around on the internet for a little bit, and I found this example about as close as I could come to anything. Now, if you want to know, and I'll try to throw the image up here for the video, the Commodore 64 C Personal Computer System Guide, Learning to Program in BASIC 2.0, has a good example of a graph in the back of the chart. Now, this graph is actually, since it's from BASIC, it's going to be a decimal, so you're not going to see the hex equivalent, but I'll translate that and show you a little bit later. And then maybe we'll go and use the calculator again and show you how to convert the values. And there's tools probably online you can find to even do it as well. But anyways, the screen memory always is going to start in the upper left-hand corner on a Commodore 64 screen. So I'm going to pull Vice up here just for a minute. It's because I'm very visual, and people who are visual will follow this. So the screen, this is the screen, Commodore 64 screen. The upper left-hand corner all the way down here is the lower right-hand corner. So this covers the entire expanse of the screen. And it goes from 1024, I believe, all the way down to 1064, if I'm not mistaken. Let me just test it real quick here. Actually, I might be off. Hold on. Okay, so it's actually 2023. So it's 1024 plus 999. And it goes from 0 to 999, which is 1,000 bytes total from 0 to 999. And like I said, this is going to be understood. If you can break this and think of this as the squares in the background example here, you should be able to understand when we write this program to the screen what's really going on. So each of these squares is Commodore 64 part of the screen here. I'm going to enlarge this a little bit more for mobiles. Try to keep that in mind here. See if I can get it on the screen. That's pretty good. So it's not all going to fit, but you can see hopefully 1024 is the upper left-hand corner. And then 1025, 1026, 1027, 1028, 1029, and so on. And it counts all the way over here until it reaches 40, and then it gets down to the next line. So this will be 1063. And then 1064 continues again at the left-hand corner, and it goes all the way across. So it works from left to right as you're writing values to the screen. Very important to remember when you're writing a value, it's just writing them essentially one after the other. And each line itself is 40. So if you want to figure out one line, you just take 40, 40 times 2, 40 times 3, 40 times 4, and that's how you do your calculations to figure out where to get things centered on the screen. So that's important to understand when we start writing the values. So we're going to just start with simple. We're going to start at 1024 and just write to the screen. And probably more advanced examples later, we could be coming down here somewhere, depending on what we're doing, if we're drawing on the screen. But we won't move too fast ahead in this video. But I wanted to show you that you can easily pick a point here. And I wish I could just click on this and show you a square. But essentially, it would pick this location here times whatever value this is down the screen from the top. So we're going to go into that graph example. So keep in mind, or the Excel graph, keep in mind that this graph here as we look at the Excel example next. And I'm going to enlarge this one too. Try to get it so you can see it all. Okay, so we mentioned earlier about the index registers, and we're going to go in those in a little example here with the program. This message text will be familiar later. It's basically just reading the bytes from the program, which we'll go over. But for now, I wanted to show you what I was talking about and how everything is broken down. Now, you see the 1024 down here. So this is just representing the screen memory. As I said, it will start in the upper left-hand corner, 1025, 1026. And this is the hex value down here. These are all the hex values equivalent to this. And if you see down here, this is the value that we're going to be planting and taking from this text, which translates it into a value that the computer can display it on the screen, which I believe is known as PET, actually, if I'm not mistaken. And each value itself is done one by one. Also important to understand that each of these could be think of like the index. And I mentioned earlier the index is like a counter. It starts at 0. It can go all the way up to 255. So X and Y cannot exceed 255, but they start at 0. So, for example, the C, if we had to think about the X counting and reaching the first value, if it wants to pull and look at the first value to print it, it's going to say X equals 0. The next value of O is going to be X equals 1. The next value of M, X equals 2. And you can see these bytes up here in corresponding, and this is the hexadecimal values, and this is the screen memory locations equivalent to this, which I'll have to show you an example of the chart, or that may not make sense to you, but it's a PET chart that's made up in your computer's memory to see individual bytes to know what to put on the screen. And these are the hex equivalents for that. So anyways, like I said, it's going through each of these values. So this will be 3, and this is, make sure I got my 3. So I got my, I got my 2s, and this is 3, counting from the index register. Got 0, 1, 2, 3, and this is 4, which is going to be byte 4 here. And then you can see the equivalent value here is 15 for the hex axis. And this is 5, index X register 5, X register 6, X register 7, X register 8, X register 9, X register 10, X register 11 as a corresponding to these bytes. And remember those bytes are those spaces I showed you earlier on the Commodore 64 screen. I'll pull the graph back up here if you need to see it real quickly. I'm just totally visual, so think of it. X equals 0, X equals 1, X equals 2, X equals 3, X equals 4, and this would be the C, O, M, M, O, D, O, till we spell Commodore 64. So essentially, those are just planting those in memory like graph paper to your screen, or painting those values to the screen. So I think it's a good enough explanation, I hope. So to save time, we're going to move on to a program example. Okay guys, before we see this example, let's go back to the chart again so we can stay consistent as we're going through it step by step in progression. So LDX, which stands for load the X register into memory, as you see here, load index X with memory. And then we have the status flags, as we always talk about. We got the negative, the zero flag, the carry flag, the interrupt, the decimal, and the overflow. And then these are broken down into tables of the addressing mode, the mnemonics, or the operand, the opcode, the size in bytes, and the number of cycles. And then for the X register, to load the X, it's made up of all these. It's made up of the immediate. If you recall, the immediate is that little hash or the number symbol after it, and the operand would be the number that follows afterward. And then we got the opcode, which is essentially just representing the value of LDX there. And then we've got the size of bytes, how much they take up in memory. They take up 2 bytes in memory. And the number of cycles they take, this is that timing, it takes 2 cycles. And then we got the 0 page, kind of the same thing, LDX operand. You can kind of see it's following the chart. To save some time here, it's going to skip. So 0 page with the Y, it has the Y after it. And then you see the bytes and size and cycles. Absolute X operand. 1 second here. Okay, so after the X register, we have the absolute, which is load the X register, the operand. And this is the one we're going to focus on in this series. Essentially what we're going to be doing, and I think I might have left out one here. Just notice that. Hold on 1 second. Excuse me. No, I'm good on that. So then we got the absolute of Y, or load the X with the operand of Y. So in this example, like I said, we're going to be using the X register, so we won't focus on these, but we're going to be basically passing values into load the X and show you how to, build it up step by step. So at the example here, I'm trying to make this consistent with one of the program examples I have here. Load the X, load the index X register with X with data or from a specified address. It copies data to the X register or copies from a memory location. The data in the memory location copied still remains intact afterward. And you can see our example here is load the X with the immediate value of decimal 0, 3, or just 3. It puts a 3 in the X register, and remember that basic X equals 3. And then we got the load the X as another example here, which putting it into the absolute value. And I'm using this example 30 to stay consistent. Actually, it's number 30, excuse me. Is consistent with the example we have that I'll show you here in a minute. And this puts the data found in memory location 48 in the X register. So the hex value of 30 is 48. And I mentioned earlier, if you wanted to see it, I'll put this over on the screen here. This is the calculator. You can just pull this up if you have Windows 10. And you can just go here, and it starts with standard, so you just switch it over to programmer by clicking on the little thing in the upper left-hand corner. And then from here, you're going to just type, you're going to want to click on the one that you want to convert, first of all. So we're going to hex, so we're going to click on that, and just type in 30, and you'll see decimal is 48, or you can do it likewise the other way around. It works both ways. Okay. So the next thing is basic looks at this as a variable of X. You could set like X to any value. You could use 2 characters for the variables in basic. So you could have like XX if you wanted, or X1 or whatever, equals peak 48 to reference that memory location. So let's go into an example now so we can see this. Okay, and you'll see some code. I always try to leave the previous code if I can on the screen where we last left off so we don't kind of jump around. Hopefully this is the same program I was using last, I do recall. So anyways, we're going to go into this one now, and we're going to begin anew. So essentially what I'm going to do is I'm going to comment this out so it doesn't interfere with our program. Let's go up here and you can click on comment. And then we'll go down here to our new line, and we're going to use our load X. Just type in load X, hit the tab key, and you just type in the number of the hash and the $sign for hex 03, just like we saw. And next, we're going to go down to the next line here. Oops, excuse me. And we're going to type in LDA for load the accumulator, tab, the hash sign, $sign 30 for our 48. And I'll just put over here decimal 48. Now, we won't see this to the screen unless we do something. And I could run this program, and we also want to make sure always have our RTS in here or it's going to crash. So we know that that's just going to exit back to basic. It won't do anything here. I could run it, but at the same time, I'm going to add the next command in because I think we're okay with these commands. I hope they by now. So we're okay with the store command, so we're going to store it into 33C. And if we go back to our calculator, for those who need to know, we could convert it here and see what memory location, which I believe is 828 if I'm recalling exactly. So we go here and we click on hex 33C, and you can see decimal is showing 828. So we're going to write it to a value so we can see this result in memory before we start creating loops and all that. So I'm going to run it now to save some time here. You'll see Vice load. Vice loaded. Now we're going to sys to our new address, which is 4096. Remember, that's the 1000 up here. And if you hover over it, like always, you can see that that's where our program counter, if you recall, is starting, where it's starting to store the bytes into memory. Starts at decimal 4096, which is exactly where we sys to, right here. Now, you didn't see anything, like I said, because it's not going to write anything to the screen. It's not messing with our screen yet. So what we're doing is we wrote to that 828, so if we peek into it, we should see the value that we stored into it last, which I believe was the 48. And there you go. So I use 828 safely because it's a area away from memory where it doesn't overwrite anything important. There's no machine language routine stored in there, and it's safe to use it. There are various location routines set aside in Commodore 64 memories that are set aside just for this specific purpose. So the next thing I'm going to do, I'm going to exit back out of here, and we're going to go into, we're going to kind of step it up a little bit here. I'm going to kind of copy this little example code. This is the example code I'm working with, by the way. It's supposed to write the values to the screen here. This one converts them to binary, so I probably won't go into that one. I just wanted to show you this to show you how to write it to the screen, but I think I'll just start consistently with the next part of the program here. So since we're safe with this, I'm going to comment this out, and we're going to begin anew again with a new loop. And remember, load the X register back to the screen, and we're going to start. Remember, it starts at 0. You could start it anywhere, don't forget the number sign, anywhere between 0 to FF or 0 to 255. We're going to start at 0 because we want to get all the bytes on the screen for the message that we saw earlier. If you recall the graph again, which I'm going to pull up here, right here, this is the values that we're going to write to this Commodore 64 screen memory. Okay, so we got the load the X register loaded, so we're now picking out the X. And next, we're going to follow consistently, and I'll put that back on the screen here, not the calculator, so I can show you what I'm doing is step by step here. I'm going to minimize this so this doesn't confuse anybody here. I think that's good right there. Okay, so next we're going to go down to the next line, and we're going to write, oh, before I forget, I talked about this, I think it was either in video 1 or video 2. This is a label. A label is just a way of referencing a memory location that can go back to that specific point in memory. Now also there's a routine called JSR, or jump to subroutine, that can jump, and also JMP for jump. That's a little bit out of this technique. I didn't want to jump ahead, but I wanted to let you know that's how those work, and you can jump to them, or you can jump to the subroutine, kind of like that Go7 basic, where you could just return off with the return. So this is necessary because we're going to be repeating this in a cycle so we can get each individual value pulled to the screen. And I'll just type the rest of the program in, and I'll explain it here shortly. If you remember, the message was shown earlier in Excel. Now I'll explain that. First, I'm just going to type it in. I put 0500 here, so I'm going to need to change this to stay consistent with what I talked about earlier. This is because I was writing it to a different part of memory. So we're going to keep it on the top upper part of the screen there. And use X. And then increment X, so we'll have to go and explain that too. There's going to be a few different things thrown in here. So this video may be a little bit more evolved, so excuse me on that. This is the only way we can really get a loop to the screen right now. But we should be good. And I'll just run the program. I think I'll just run it first here, and then afterward we'll just go into the explanation. I left off the message here, so I'm just going to copy this up here real quickly. And just minimize this again to eliminate confusion. There we go. Okay, so we got our message. And then after our message, as you recalled earlier, we use a command called text. And then we write that value in text to the screen as we want to see it. Commodore 64. And I'm going to run it, and then I'll explain it. and you just run by hitting this little upper arrow here in CBM Prg Studio, we got an error. Hold on. So apparently it didn't like the space between this, so you don't want to put spaces between the X. CBM Prg Studio will complain. So now we're going to run the program. Hopefully it doesn't crash on me. Now you don't see it in the screen because what it's done is it's converted this directly into screen memory. But if we hit the Control key, and I believe it's the Shift key, you'll see Commodore 64. So we'd have to convert these bytes down to different values in the PETXC character set. But I wanted to show you, if you press the Control key and the Shift key, you can kind of see the message on the screen. But later, if you want to get the actual values without having to convert to the second character set, you'd have to just change the values on the screen. And maybe we'll have time for this, maybe we won't in this example. I just wanted to show you that. You might also even be able to use the byte. Let's see if the byte will do it. I think I tried the byte and it might do it, or it might not. Let's see. It's worth a shot in the dark, I guess. Nah, the byte doesn't do it either. It's kind of doing the same thing, matter of fact. Yeah, it is. Oh, and we're leaving out the 4 here, so I probably need to increase the loop here. Let me also put this back the way it was. Just run again here. It's a test. Yeah, we're leaving off the 4. So what we need to do is we need to change this B, and I'll explain this in a minute, and put it up to a C, so we increment to the next value of that X, as we saw earlier in the chart. And I'll just run it just to make sure it's consistent with what we're trying to do. And run the program. And there's the 4. You see how the 4 appeared? So now, what's going on, you're probably wondering. Let's break this down. Analysis. And we already know how, hopefully, we load the X register, starting with the central point of 0 to get the very first byte on the screen, as we saw earlier on the example of the Excel chart. We saw all the AXI values laid out, and we saw the bytes 0, 1, 2 from the top to correspond to that text on the screen, which is what this text is doing right here. So what we're doing is we're taking the load the value. Remember, it's storing individual bytes, or if you will, numbers, characters, symbols, or whatever, onto the screen. This is all made up of the PETXC chart. And what it's doing is, if you remember the loop here, which will come to an example in a minute, it's going to this loop, this label down here called message, and finding this reference point in memory. Since it's going through in here, it's reading these, the compiles is going through these line by line from left to right and read them into memory to get each of these individual results here. So it's basically reading this line by byte by byte by byte. We saw that this was byte 1, byte 2, or byte 0, byte 1, byte 2, and so on. And that's what it's doing, is it's referencing that label so it can pick off each of these values to get a print result to the screen. Now that's what load does. Now this, so far, this right here hasn't done anything. It's just loaded the values into memory. Now what it's essentially done without the loop, if we left this RTS off and we didn't have any of this other stuff, and just like, for example, we commented out all these lines here, it would only read the first C on the screen, if I'm not mistaken, if it reads it backward or whatever. It would read the first X on the screen since it started at 0. And then what this next one does, increment X, is moving the counter up by 1. So we started at 0, and now the counter has incremented to 1. Just like counting from 1 to 10 or 1 to 255. In this case, we're counting up to the result of this limitation here, which will come to an example. But I want you to know, increment X means increment and get me the next X value found in memory, so I can keep reading the results of these bytes directly to the screen in this example. And the next one is called compare X register, and what it's doing is it's reading and checking this value in memory. So this is going to be a little bit advanced. You can bear with me a second here. It's saying, what is being found in X? Now remember earlier, X we know started at 0. So it's saying as it goes through in the increments, and I'll just put this down here as an example to show you. X, the first time through the loop, after it hits X, is going to be equal to 1. So now this thing is saying compare the X value in memory to see what the value is for that X register. Is it a 1? So what it's doing is it's counting through this loop and it's saying, is it a 1? Have we reached a 1 yet? Yes, we actually have in this example, but this is not saying compare 1. Now, if this were a compare 1, it would say, yes, we found it. But in our example, we're using C, which does not represent 1. So if we go back to our little decimal calculator here, or hex calculator, excuse me, and we convert this value C, you can see it's 12. So it's counting up from 0 to 12, or 13 bytes total in memory. If you count these 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I may have been off here. Let me just double check myself here for a minute. Yeah, it's actually 11. So what it's doing is it's basically, the C is needed to get that next value of the result, which is why we only saw the, when it did Commodore 60, and it just said Commodore, and it said 6 on the screen, but it didn't have the 4 because it wasn't reading the next byte, which is why I incremented here. It's because of how this increment X register works. But point aside, we could make it drop off if we just did 1. We'll run an example and just to show you what that means here for a minute. To show you. Like I said, an analysis. It's all about analysis. Now, if I shift again, you'll see only the C appeared on the screen. It's also getting the inverse value of C, but we can still see that it's getting the C. Now, if we change this to 2 and run again, you'll get the idea of what's going on, hopefully, here. Oops. And shift again, you see that now it's read 2. It's read the C, and it's also read the O in memory. So what it's doing essentially here is it's going byte by byte by byte, as I said, until it reaches the result found in this compare register. Say once X equals, I'm going to change this back, to our C, which we know is decimal of 12, then what it's going to do is it's going to look at the next instruction below it, which we'll talk about. This one is the branch I talked about a little briefly earlier at the beginning of this video. It's called branching, basically to figure out where is this value in this index register. So what this stands for is branch not equal. It's saying, is the branch not equal to 12 in this example? If it's not a 12, then what it's going to say, we've triggered, I believe this is a flag in memory, and it's going to go back here and say, oh, you know what? We're not done with these bytes yet, so we need to go back and we need to get more. Think of that circle. So basically, essentially, it's writing these values to the screen in a loop increment, kind of like the for next loop in BASIC, how you do for x equals 1 to 12, and you maybe print something in the middle, and at the end you'll have a next statement to make that next go back to the for and keep repeating that until it's essentially done. And that's exactly what's going on here. Hopefully that makes sense. So it's saying, oh, we're not done, so I'm just going to say loop back to, now I need to expand this just a little bit here. I'm going to move some things around here for a minute, because I can enlarge some things here. So loop back to loop. Well, I should say go back to loop. Loop back to loop is kind of silly. So go back to loop, which is basically this area right here, or this address in memory. So essentially it's looking at the bytes as it's scanning through the compiler, and it's going right back a little bit earlier to where this loop was stored earlier in the text. And it says, there's a loop bound here, so I'm going to go back and I'm going to keep repeating these results until we've written all of these bytes on the screen. And we could, example, do this again by cutting off the C here and just putting in an A, and I think it'll probably print the Commodore only to the screen here if I do it right here. As an example to show you how that branch not equal works. I don't know if I can make this any bigger either. I was going to try to maybe expand these a little bit. There we go. So with system 4096, there it is. So it printed the whole thing for Commodore, but it left off the space. It may have got the space, but you can't see it if it did. And it left off the 6 and the 4 because our bytes have been reached. In this example, we reached A, which is, 10. Or, let's see, yeah, 10. Because if you go back here to our chart here, and you just type in the hex value here of A, you'll see it's decimal of 10. So that's how the loop works, and that's how the index X register works, by reading them one by one. And if, again, we recall our chart here, index byte 1, this is the X register. So I'll show you here step by step again, break it down. X equals 1, X equals 2, and actually I did this wrong. X equals 0, excuse me. X equals 1, X equals 2, X equals 3, X equals 4, X equals 5, X equals 6, X equals 7, X equals 8, X equals 9, X equals 10, and X equals 11. And then we'll convert these down here to hex next. I could show you that. x equals 0, 0, x equals 0, 1, x equals 0, 2, x equals 0, 3, x equals 0, 4, x equals 0, 5, x equals 0, 6, x equals 0, 7, x equals 0, 8, x equals 0, 9, x equals not 10, but this is hex, A, because we're starting over, and we're beginning with A now. If you remember, if you want to watch the first video on hex, you can learn about that. X equals B for the next value. Now keep in mind that this B here, very importantly, pay attention to this B here, and where it is in here, in the chart. So this is a good chart. If you look, I'm going to save this, and maybe I'll do an upload to GitHub so you guys can see this. This B, if we go back to our program example, you'll see, and actually, in this example, I changed it, so let's put it back to B. Sorry about that. Or C. Because if we put it to B, it's not going to get the last value. So essentially, it's just reading out here. We could say x equals C or whatever, because it has to get that last value to get the full result to the screen. This is how the screen memory works. But essentially, it's lining up these values by figuring out what's in 0, what's in 1. And I could show you here by cutting it off halfway. We'll set it to 5. Let's see if that'll work here. Just set it to 5. Hopefully it'll just put that commode up to the screen. Commod or whatever. Sys back to memory. And there you can see, actually it left off the D, so it got to the O. So the 5 essentially is just looking at the value right below it because of the way this register increments in the memory. So not to confuse you, but you can see step by step here, 0 is going to be the C, 1, and that's just how the loops work. So hopefully I've hashed that enough that you can understand how that works. Since this video is limited for time, I think I'm going to save the Y register into another video. Maybe I'll talk a little bit more about the examples down in here if I can, without jumping too far ahead, but I've got a lot of stuff in here. So we might, if I don't have the thing in here, I might need to break another video of it. So I may, actually I got these on the side here. Let me see if I've actually put this on here. I may not have to compare X register. I have it down here. So let's go back to the program example line by line. So we learned about load X, we learned about load A, we learned about store. Now increment X, we can go down here and we can find it. We can click on it and go right to it. So we can see index X is address in mode. And these are the tables I have for assembly language from or form. Opcode, the size in bytes again, the number of cycles. So index X is implied. So basically it applies directly to that value. And this is the basically the machine language component of this, obviously. The opcode is going to be the value that this represents in the compiler's memory as it's reading those bytes in memory sequentially, which is E8. If you need to know, again, you can go to your chart here or any chart that you have a conversion, just type in E8. You can see it's 232, which is the decimal equivalent for increment X. And the byte, the size it takes up is 1 byte, and the number of cycles is 2, which is our timing thing. And down here broken down, increment X is increment index X by 1 to start with. It just increments each time 1, 2, 3, 4. There's ways of making it skip ahead later, but you have to kind of use tricks for that. We won't go into that, but for now we just know it's going in order. So this program will set the index X register and increment that value. An example here is, this is a different example, is load the X register at the immediate value of the string of FF, which I put 254, it's actually 255, excuse me. 255 to 254, FE, not F3. And then not decrease, of course, increment. We'll learn about those other stuff later, how to decrement and make it go backward. But this video, like I said, I'm going to break it down basis by basis, step by step. Increment the X by 1. So now the value contains 255 because it started, FE is 254 as you can see over here. And it incremented by 1. Remember that the X value goes from 0 all the way up to 255. And the next value from 254 would be 255. Of course, earlier in our example, it went from 0 all the way up to, what was it, 12 or whatever, B. And it just essentially writes those values to the screen in that example. But this example, it's not writing. It's just showing you a different example that you can use for load the X. You can put any values in here as long as they're between 0 and 255. And the basic example, if you had to use a variable X equals 254 or X equals X plus 1, the result is X equals 255. Now I'm going to run out of time here, but the compare X, I'll try to jump ahead here real quick. CPX, these are the addressing mode, same thing, the same values, and you got the immediate, so you can use compare X for the immediate value on the operand, and you see the operand, the opcode in bytes and cycles, and a 0 page, which we haven't covered here yet, but you can compare it directly to 0 page, and you can also compare it to absolute value, which we haven't done here. These are going to probably be saved for later videos. Again, machine language, step by step, we're breaking it down for you. So the next one is branch not equal. And here's the chart for that. Addressing mode, assembly language form, opcode bytes, number of cycles, and branch not equal is relative. And this is an example. Branch not equal to the operand. Remember, in this case, the operand would just be whatever you put in this value right here. It's the operand, and it goes back to this loop example or that addressing. And in this, the opcode, the bytes and cycles, and so on. And there's other stuff which we'll cover later, like equal and different things, but I wanted to stay consistent with that simple example and not go over on this video. So we ran out of time here. I try to keep these as much to 45 minutes. Whew, that's a lot to cover just for one simple example of a loop. So if you have any questions, go ahead and throw them down in the comments. I'll try to respond accordingly. But remember, it's just incrementing those values step by step to check those individual bytes in memory to see what can be placed on the screen next. So we just use those for example, a screen memory, but you can use those to compare. You can do a lot of things with the X. It really can get a lot involved, and I just wanted to start simple and try to break down simple concepts. As we start writing more larger programs later and start reusing a lot of the stuff like the increment, decrement, which we haven't covered yet, and branch equal, branch plus, and whatever, you'll start seeing how they work. As we start going more and more into code examples, more and more we do it, the more it's going to start sticking to you. So this video is at 42 minutes, so I hit a pretty good timing here, so I'm not over in this video. I'm pretty happy with the results there. So I'm just going to quickly show you, this is the book that I was getting the examples from, the Commodore 64 Programmer's Reference Guide. It has some examples back here. I was trying to show you this earlier, but this is the hex screen. This is the AXI values I was trying to show you earlier. This is the AXI values. If you look down here, I'm going back to my old dumb ways of doing it. These are the individual characters here, and the C is the 3, and those are those equivalents we were writing to the screen earlier there. So I don't know if you can see that. You can get a PDF. It's not totally necessary for me to, splashing books on the screen like that for you. But here's an example also of where you can find. You can get these online, but this is where I got that example of the chart. It displays the memory on the screen here, and if I could find it quickly enough here. It's also got the AXI code, but here in the back here, this is where the screen memory is, and I'll just move it in there just a little bit. Camera's probably not going to grab a focus. That was the example I showed you in Google earlier, so it's not totally necessary, but I want you to know that's where I'm getting these examples from, just from my experience. Always great reference book once you get into more advanced concepts and whatever. So I hope you guys enjoyed this video. I appreciate your comments, feedback, and your subscription. It's very important to help me grow this channel and move it along at a consistent basis. Now, I'm glad I'm able to stay more controlled. Hence, this stuff is pretty amazing. I mean, I've only tried one pill today, and I already see the clarity and the focus and concentration that's going on. Usually at this time, I'm a little jumping around watching videos, jumping back over here, but I'm not. I'm staying focused, and this is awesome. So I think this might be working for me. But time will tell. Anyways, thank you so much. I appreciate everything. I'm glad to be back on track, and we'll keep moving the series along. And let me know what your thoughts are. You guys are wonderful. Love you guys. Take care.